So in this video, I want to talk to you about a special type of rational function, and it's going to be, the graph is going to end up having something called a hole. But what I want to point out to you in this expression, or this equation that I've written, is that there's a term on the numerator that's exactly the same as the term on the denominator. So this video relates to those typical situations. Okay, so the way I want to start is we can look at this function and go through the same types of questions we've been asked. So if I wanted to know what the domain is, my strategy is what it has always been. I'm not going to allow the denominator to be 0, so I cannot let x be -2, and I also cannot allow x to be -1. So my thought process is x is not equal to -2, x is not equal to -1. And on the real number line, that's saying I punch out at -2 and I also punch out at -1, but everything else is okay. So in our class, we're always giving domain as interval notation. So, -infinity to -2, and then union -2 to -1, union -1 to infinity. So this would be the answer to the domain. So same as we've done before. Now, when we're asked about zeros, in previous examples, we've simply looked at what values make the top of the fraction or the numerator 0, and it's the same idea, but the one caveat is now x cannot be -1, so that is not going to contribute a 0. So the only 0 is x equals +1. And let me just put in parentheses, the reason is since x equals -1 is not in the domain. So that's really kind of the first change we've seen with functions of this form. So our next question might be, what is the y-intercept? And then just so we have it on the slide, I'm going to rewrite for us the function we're talking about. And anytime you're asked for a y-intercept, not just for rational functions, but for any function, your strategy is going to be set the x's all to 0. So this is 0 - 1, 0 + 1, and then 0 + 2, 0 + 1. And if I clean this up, I think I'm getting back -1/2. Now, because I'm being asked for an intercept, they're really saying that they want a point back. So all this work is great, but what we want to say is that the y-intercept is this specific point that lies on the y-axis. So part D is asking me, do any terms cancel? And this is what I alluded to at the beginning, that this term is the same as this term, so I can think about just eliminating them. So yes, and what we can say is that we now, in this reduced form, can just think about this. Now, everything we've already learned about graphing functions of this form will apply, as long as we remember that at the end of our graph, we have to punch out the value x equals -1 and whatever y value goes with that, because of this originally being in the denominator and affecting the domain. Okay, so the next question is, what is the coordinate of the hole that we're punching out? And we know from what we've crossed out that the x value is -1. And I know that because if x is -1, that's making this guy 0. So that's not okay for being in the domain of the function. So the way I'm going to get the y coordinate is I'll just plug it into the x coordinate into these two remaining terms. And so what I'm getting back is the y coordinate that goes with that would be -1 - 1 over -1 + 2. And what I've done, just to be super clear, is just for these two x values, I've plugged in this -1. So if we go ahead and crunch that down, on the numerator, you're getting a -2, and on the denominator, a +1. So the coordinate of the hole that we're punching out is -1, -2. And again, I'm giving it as a point because I'm asked for the coordinates. Okay, so this guy is the hole. And we'll want to remember that when we are at the very end and doing our graph, we'll want to punch that out. Okay, so the rest of the problem is going to progress just like you've seen previously. So we have some questions about a vertical asymptote. And I will remind us our function that we're talking about. We've gone ahead and We've crossed out the similar terms, so we'll just remember that our domain is restricted, but I won't rewrite those two terms that we've crossed out. And we know that the vertical asymptote is coming from whatever x value makes the denominator 0. So I'll write it as, x is -2. And this is really the equation of the vertical line going through the x value -2. And so what I mean, we'll do a lot more work with this, but if this is -2, what we have is this line here. So this equation of that vertical line is x is -2. So then we'll go ahead and get a sign chart going so that we can discuss the behavior along the vertical asymptote. And because I've already canceled out the term that was identical on the top and the bottom, my sign chart only needs to have these two terms. So it's made things shorter and easier for us. So we have these terms. And what I want to do is I'm going to mark this guy is, 0 at -2. So I'll put a 0 there. And that's corresponding with the vertical asymptote I have drawn. And then we also have a 0 at 1. And I'll just put it on the graph so you're seeing what that's saying. Now I'm going to fill out each of the rows. So negative up across 1 and then negative across here. And now I'm going to multiply to get the sign of f of x. And we're getting a positive, a negative, and a positive. So if we're talking about behavior along the vertical asymptote, we need to look to the left and to the right of this dotted green line. So the box to the left has a plus, the box to the right has a minus. And the way we'll capture that is we'll say as x approaches -2 from the left, that's the little minus sign up there, f of x goes to positive infinity. Just to be clear, the reason this is a positive is I'm in the box that's to the left of -2. And then similarly, as x approaches -2 from the right, f of x is going to minus infinity. And why I'm saying that is if I'm on the right of -2, I'm in this box, and I have a minus, so that's giving me this minus infinity. So putting that information here just so you see what this is telling us in terms of the graph gives us this behavior just near the asymptote. We don't know what's going on away from it. But this would be the proper language that we're looking for. So part H is asking about the degrees of the numerator and the denominator, and they're the same. So I'll write that, and we could answer this question either in the original form. I'll just rewrite what we had. We had this. So here, the degree of the numerator would be 2 because you have an x squared, and the denominator also is 2. But if we've gone ahead and canceled these terms, which were the same, okay, there's the red, the degree would be 1 and 1. But in either case, the degrees are the same. And the reason this is helpful is I think part I is asking us what's the end behavior, the long-term behavior. And this is where we say as x goes to infinity, f of x goes to, we'll figure that out in a second, and as x goes to minus infinity, where does f of x go to? Now, if the degrees are the same, what we have to just look at is the ratio of the leading coefficients. And really there's a 1 on the top and the bottom that we're not seeing. So both of these are going to 1. Now, if the degrees were not the same, I would not be able to conclude this. So part J is really just repackaging your answer from I in a different way, and it's about asking about a horizontal asymptote. And that's the equation of the horizontal line that my function is hugging out on the ends. And I'm putting this in blue, so you're seeing that the reason it equals 1 is because that was the answer we got in part I. And now the last thing that we need to do is a quick sketch. So maybe part K. And you can definitely sketch this by But I've just gone ahead and put this into Desmos for us. Now, the one thing that Desmos did not do is, if you recall, there's a place that we have to make sure we're punching out. So I will just use this bright orange color so you can see it. And we knew from our previous result that the coordinates of the hole were -1, -2. So what I need to do is go on my graph, and this is now a hole. So really I want to come and punch that out, and I'm not sure, maybe if I use the white I can color over. So basically your function looks just like the graph of x minus 1 over x plus 2, except you have a hole punched out at the coordinates that I had, where I had to exclude that x value from my domain.